Okay, welcome everyone. Thank you for coming to the EOL seminar today. Today our speaker is Emma Järvinen from the Karlsruhe Institute of Technology, where she's currently a postdoc. And she's studying the optical properties of clouds and aerosols. She got her PhD from KIT in 2016 and has extensive experience flying around on various research aircraft. She participated in 2 EOL campaigns, both Aristo 2016 on the C-130 and Aristo 2017 on the G5, which just happened. And most recently, as in a couple days ago, was participating in A-Cloud, which is taking place in Longyearbyen, Svalbard, on some German research aircraft that are modified DC-3s. So we're very glad to have Emma, and I'm looking forward to your talk. Thanks.
Okay, thank you for the introduction. Yeah, it's on, but are you hearing me okay? Yeah, good. So today in this talk I will present some of those results that I've been gathering since 2014 with different research aircrafts. And the theme is to really understand now what are the light scattering properties of Cirrus ice crystals and how they are dependent on the particle morphology, on the particle shape, and most important on the particle microscale structures. That is maybe a topic that hasn't got that much attention lately, but I hope after this talk you will be all talking about ice crystal surface properties. And I'm trying to discuss my results and their implications for the radiative transfer and climate modeling. But to start, I wanted to introduce you how ice crystals have been seen in optical models and in scattering models. So the most simple model for an ice crystal, also the first one, is a sphere, because just it has the highest symmetry and you have an analytical solution from the mean theory. But of course, atmospheric ice crystals are rarely spherical, so then there was a need for more sophisticated models. And the next model was an hexagonal crystal. But again, we don't just have hexagonal columns in the air. So then the model development tried to develop in the direction where we have more complicated models to really represent the atmospheric ice crystals. So in the next models, we had already a different combination of different habits, different shapes for different sizes, and also tried to include some features such as hollowness within the ice particles. But then it came an era where laboratory measurements started giving evidence that actually we don't just have different habits for ice crystals, but we also have different microscale structures such as surface roughness. And then there was a question, should we also include this one to the models? And there was a development towards where we had also different degrees of surface roughness. So we have different shapes and different degrees of surface roughness, so it's getting really complicated. But now if you look at the angular light scattering properties of these different ice crystals, so we have here from mean theory, from the spherical droplets, maybe the color is a bit bad. And what we see here that we have a totally different angular light scattering as we have for the ice particles. So yeah. And what we then see also is that there's also a difference if we have these pristine ice particles or if we have these roughened ice particles. So here, these are from Bin-Yang's database. The pristine ice crystals still have some features like the 22-degree halo, the 46-degree halo, and we have the ice bow. Whereas if we have these complex ice crystals, we have a flat and featureless scattering phase function. And now if we are talking about climate models, we need to somehow parametrize this. And how it's done, it's using an asymmetry parameter that is just an integral over the cosine-weighted scattering phase function that is giving us the symmetry of the scattering, meaning how much light is scattered in the forward direction versus how much light is scattered in the backward direction. So if we want to know how the clouds are reflecting, we need to know this. And now, if we look at the symmetry parameters for these smooth particles versus these complex particles, we have a small difference of 0.02 maybe. And you might now ask, well, is this a significant difference in the symmetry parameter? But the answer is yes, it is. And there was a really nice modeling story from Bin-Yang's group where they took the CAM5 model and they just changed the ice crystals within this model So in one run, they used pristine ice crystals with asymmetry parameters above 0.8, and in one run, severely roughened crystals with asymmetry parameters slightly below 0.8. And what they got is now just changing the surface features of the ice crystals, a difference in the net cloud radiative effect, almost 1.5 watts per square meter, that is comparable to the positive CO2 forcing. So indeed, it is really important to get the asymmetry parameter of the ice clouds or the clouds correctly. But now the question is, okay, we have some evidence that there might be surface roughness, but is it really relevant for atmospheric ice crystals, or is it just something we produce in the lab? So we have gotten more evidence after we have polarimetric satellite measurements. So now if you look at measurements of polarized reflectivity in the near backward scattering and try to simulate these measurements with different ice crystal models. So by using the MODIS collection 5, that is just a collection of pristine ice crystals, we really don't capture the atmospheric measurements. We have a lot of features in the polarized reflectivity, and they are not just representing what we are seeing. That was also the motivation to develop the MODIS collection 6, where we have only roughened ice crystals, and also they have given up these different shapes and are only using one ice crystal shape. And now with this model, we are really representing the atmospheric measurements. We also see that we changed the asymmetry parameter of these clouds quite much. So compared to the MODIS collection 5, we don't have any size dependent in the asymmetry parameter, and we are at low values around 0.75. And again have this featureless scattering phase function. So yes, we have some indirect evidence that indeed these surface features might be important, but there was long no in-situ measurements to prove that this is really the case in the atmosphere. And the question still lies, what is now the cloud asymmetry parameter? So in my talk, I'm going to first discuss how to quantify the ice crystal complexity. And then before I'm showing the field experiments, I'm going to discuss some experiments we did at the cloud chamber in Karlsruhe, where we studied what is the origin of ice crystal complexity and what is the link between the particle morphology to the angular light scattering. Then I'm going to go into two field studies that we did with the HALO aircraft. One was in Mid-latitude and one was in Brazil. And then I'm going to sum up all of the measurements we did to get kind of a global picture of our findings for the crystal complexity and for the asymmetry parameter. And also discuss what happened when we put our results in a global climate model. And just as an outlook, I want to then discuss maybe some new directions for atmospheric measurements with in-situ probes. So in this talk, I'm going to divide crystal complexity into two categories, a large-scale complexity and a small-scale complexity. And a large-scale complexity, I mean complexity that is in the scale that is larger than individual ice crystals, for example, aggregation. And there's also, there's already an attempt to quantify this complexity using a complexity parameter defined by Smith and Heimsfield, where we just take the projected area of the particle divided by the square of the area ratio and the perimeter of the particle. And it's kind of giving us now the degree of aggregation or degree of complexity within these ice crystals. But what we see here, if we now plot this complexity parameter as a function of maximum dimensions, we see that single habits, they have pretty steady complexity values below a certain threshold, and if we have aggregates, we have complexity parameters higher than this threshold. So we can use a threshold to define if a particle is an aggregate or not based on these images. I'm presenting this because I'm going to use it later in my talk when we study in the tropical systems aggregation. But then what is now more difficult to quantify is the small-scale complexity of the ice particles. And why is it, so first of all, what I do mean by small-scale complexity. So it can be surface roughness, or it can be also other features that are smaller than the individual ice crystal size, for example, also hollowness, or we could also calculate polycrystals in this category. And as I said, there has been a lot of laboratory studies to study it. We have ice crystal models that are using small-scale complexity, using surface roughness, and we have studies with ice crystal replicas. But not like with the large-scale complexity. If you now take a complex small ice crystal and take an image using a cloud particle imager, we cannot now, based on this image, based on the resolution, say anything about these features that are seen here in this image. So it's evident that we need another approach to really try to quantify the small-scale complexity of these particles. So then what's better than to borrow methods from other fields of physics? So there is a method that that is used in industry, quality control applications for determining, for investigating roughness surfaces, is when you illuminate a surface with a laser light and measure the spatial distribution of the scattered light. And it has been shown that measuring such scattering patterns and analyzing these scattering patterns, for example, using a gray level coherence matrix method, that's a statistical method for exactly for studying these image structures, is that what we get from this analysis a complexity parameter that indeed is linearly dependent on the actual surface roughness. So this was a work by Lu et al. So if we are using a laser light, here we use 500 nanometers, we can indeed quantify surface features that are approximately around the wavelength of the used light. If we have features that are much larger than the used wavelength, this method is saturated, but for this scale, we can really now quantify what is the complexity within these different, what is the surface roughness in this case of these surfaces. But then the question is, okay, this was for two-dimensional surfaces, would it also work for three-dimensional atmospheric particles as this one? And yes, it will, because also from this particle we can measure the spatial distribution of the scattered light and get these sort of scattering patterns where we can then analyze the complexity. And there is an instrument that is doing this. It was developed in Hertfordshire, and it's called the SID3 detector, and some of you might have also heard from it. So now we have a method to really study also small-scale surface features, but since there's not many SID3s flying around, and before using it in the atmosphere, we wanted to quantify the method in our cloud chamber to see if it's really working or not. So we did some simulations at the AIDA cloud chamber that is about 84 cubic meter aluminum vessel. It's located inside like a big fridge, so we can cool it down to -90. And we can evacuate it and create adiabatic expansions to simulate cloud formation. And we can do it with different pumping speeds to simulate different upward speeds in the clouds. And what we did is we tried to then simulate Cirrus conditions at Cirrus temperatures and try to really then quantify, okay, how is the growth conditions of these ice particles now created, how their morphology is developing. So we created experiment series where we first created the ice particles by heterogeneous nucleation on different aerosol particles. But since the nucleation process is now dependent on the aerosol properties, so we get the growth at a distinct supersaturation that we cannot control, we thought, okay, let's supplement the ice particles to get rid of any features that might have developed in this initial state of the growth, get like a blank piece of paper, and then after this one, grow the ice crystals at distinct supersaturations to really then now investigate how these morphology is developing at different growth speeds. And we can do this in cycles as long as we have ice crystals in the chamber. So the first experiments were done by developing vapor chrome crystals at the temperatures -40 and -50 degrees, where we have columnar ice crystals. And we can see from the scattering patterns of these individual ice crystals the 2- or 4-fold symmetry. And what we now here see is a graph where we have the saturation ratio that we use to grow these ice crystals. Each single point in this graph is one experiment. And here we have the complexity parameter. And here we have ice crystals at with different complexities. And before to go in the graph, so what we just see with the naked eye, that if we have a higher complexity parameter, we produce ice particle scattering patterns with much more speckles, whereas if we have a lower complexity parameters, we see more of the symmetry within the ice particles. But what we now see is also, if we now look at the individual experiments, what we did is that we have a clear trend between the saturation ratio that was used to grow the ice crystals and the complexity parameter. And we have here now 2 curves because we did it at 2 different temperatures, and at warmer temperatures we have more water vapor available, meaning the ice crystals are growing faster. So then to try to summarize these 2 curves in one single curve, we thought, okay, let's parametrize the growth conditions using a parameter that is called the condensable water vapor mixing ratio. That is just describing how much excess water molecules we have within the gas. So these are the water molecules that are available then to condense on the ice crystals. So just to combine now the saturation and the temperature, and now we get one linear dependency, meaning the faster the ice crystals are growing, the more complexity they are developing. And also, then to see what is the complexity within the ice crystals is that we know that at these saturation ratios, or at these, we are in the hollow column regime, and using ice crystal replicas, we were really able to see how these ice crystals were growing the hollowness. Based on this method, we couldn't really investigate if there was surface roughness because the replicator method is not good enough for this one. But at Willis, we know that there was something going on, or also if the ice crystals were growing fast enough, the hollowness turned into air inclusions, air bubbles. Okay, so now the question is, okay, what does this mean for the light scattering properties of these ice crystals? So what I did, I also measured the angular light scattering properties. For each experiment, we didn't have the instrument available, but for these 3 experiments with different complexity values, we had a polar nephelometer, where we now measured the angular light scattering within the whole cloud inside the chamber. So these are the results. So these red ones now correspond to these 3 experiments, and just to also compare, I had one that is representing an angular scattering phase function of a droplet. So what we see is a flat and featureless scattering phase function with a higher backscattering compared to the droplets. But interestingly, we thought that, okay, we should see some difference in the angular light scattering by changing the complexity of the ice crystals, but all of these experiments showed exactly the same scattering phase function. So, okay, we thought, as seen in these images, so if we have enough complexity within these ice crystals, maybe it's enough to destroy kind of the light scattering properties, and so we would always have one uniform angular light scattering properties. We didn't know, but we thought, okay, at the point where this is happening, we defined a threshold value for the complexity, saying that if we have complexities higher than, if the complexity parameter is higher than 4.6, we would expect to have similar angular light scattering properties that are now independent of the further increase in the particle complexity. And that was just a theory that we were thinking about in these laboratory measurements. Okay, but then we don't only have vapor-chrome columns in the atmosphere, so we also did some simulations to simulate convective systems and frozen droplets to really also understand how they are developing. And there is what we did is, as we started with a liquid cloud, and then we froze it. So we first had liquid droplets, then we froze the droplets. They all developed as a frozen droplets, and then we once sublimated the cloud. And this kind of proves the point that I was talking about in the beginning, because these are the ice particle images from the experiment. So we really don't see much difference of these images from the beginning of the experiment towards the end of the experiment. We have just small spherical plots. But if we now look at the scattering patterns at different phases of the experiment, as said, we have first a droplet with concentric rings according to the mean theory. Then as the droplets freeze, we get these really complex speckled images indicating now a high degree of complexity. And then as we sublimate these ice particles, we get these rings back. First we have some deviation, but at the end we have scattering patterns that cannot be any more resolved from the droplets. But these are still ice particles because we are still at minus 40 degrees. So indeed, these ice particles that were measured during the growth phase, although looking at the same in the images, have totally different surface features than these ones that we found in the sublimation. So we created a model that if we freeze these droplets, we get these frost balls that are really complex. And only if we sublimate these frost balls, we can really get, again, spherical ice particles that are indeed not only spherical in the cloud particle images, but they are also optically behaving as a sphere. And then coming back to the previous laboratory measurements where we said, okay, if we have complexity on the particles, they have always shown the same scattering properties. And now you might say, okay, that's clear because they are all columns. Why should we expect that spherical particles, if they are complex, would show the same scattering features? But to convince you that our idea was not so stupid, I have here the angular light scattering function of the columnar ice particles and again droplets. And if we now study the angular light scattering properties of these smooth ice spheres, they indeed are optically spherical, having almost the same scattering response as a droplet. But if we look at the angular light scattering properties of these complex spherical ice particles, we have almost exactly the same angular light scattering function as in the case of spherical particles, so columnar particles. So the question is really, if we have enough complexity within the ice crystals, it seems that the shape of the ice particles doesn't anymore matter, but we have always the same angular light scattering properties. And with this knowledge, we went into the field and did campaigns, and I'm going to show you results, as said, from the HALO aircraft and from the G5. So in the first campaign, we were in the mid-latitude, and we did have our polar nephelometer, but it wasn't really working at that time, so we were able to only investigate the complexity of the ice crystals. So we were flying in different meteorological situations that we can find in mid-latitude. We had warm conveyor belts with continental or with maritime origins, or we had also jet stream Cirrus. And we were trying to not figure out how then the ice particle morphology in these different systems might then be different. So I'm going to skip all the other microphysical measurements and only show you how the small scale complexity is now in these different systems. So again, we have here the complexity parameter. Increasing complexity means increasing complexity parameter means increasing complexity. And here we have the different cases. So we have continental warm conveyor belt, maritime warm conveyor belt, jet stream Cirrus, and contrails. And to highlight the complexity threshold where we thought, okay, this has something to do with the uniform angular light scattering properties, is what we see now here, that if we have continental influence in these systems, we have much smoother ice crystals, and majority is actually below this threshold, which could be explained because we have now more heterogeneous ice nuclei also coming. Whereas if we have marine warm conveyor belts, but still the air coming from clean oceans, we have much more complex particles, much more of these microscale complexities in the ice crystals. Whereas if we have particles that are prone in jet stream cirrus that have no updrafts or no convection, we have the highest complexity within the ice particles. And then there's contrails that are pretty much all over the place, so they are pretty difficult to quantify. Yeah, but what we see here already is that usually we have pretty high complexity values. In maritime and jet stream cirrus, the median complexity is always above these thresholds, and it's approximately comparable with our simulations with rough-net ice crystals. But we didn't have a polar nephelometer during this campaign, so we really couldn't say what this means now for the angular light scattering properties. And then later, we did a campaign in the tropics, where we were now studying convective systems. So we were studying outflows and also in-situ cirrus. And we're trying to now look how then both the microphysical and angular light scattering properties are depending in the pollution rate of these outflows, or if they are outflow or if they are in-situ cirrus. So just a maybe interesting detail is that we did find a clear separation of the ice crystal habits in situ cirrus or in outflows. This is nothing new, but at least we had cases where we had mostly columnar or bullet rosettes in the clouds, and we had cases where we had a lot of plates and plate aggregates. So we could study two totally different cirrus types. We also, based on these images, studied the large-scale complexity of these systems. And so here we have the maximum dimensions of the particles again, and the complexity parameter now from the Smith and Heinz field study. And what I here wanted to show that after a certain size, we are dominated by the aggregates. This is pretty much similar that have been observed in other tropical campaigns. So let's say particles larger than 100 micrometers are complex because they are aggregates. But in the small particle range, now we can use the C3 measurements to also determine if these smaller single habits also are complex. So again, we did also this. And here are again this histogram of the complexity parameter for different cases. But what I want to here highlight is that if we have an in-situ cirrus compared to the outflows, again with totally different ice crystal habits, we really don't see that much difference now in the small scale complexity. And if you look at the threshold, meaning we have had always in these tropical campaigns, independent on which system we were measuring, a high degree of ice crystal complexity with the median values always below this threshold. And again, it's comparable to our laboratory simulations with complex or medium complex ice crystals. And now to go into this angular light scattering properties. So as we found in the laboratory, indeed, if we look now the angular light scattering of these always complex systems, we have always the same angular light scattering function as in the lab. Even if we have in-situ cirrus with columnar ice crystals, or if we have these outflows with more plate-like ice crystals. So this now really gave us the idea that really the ice crystal shape doesn't matter for the light scattering properties if we have enough complexity within these ice crystals. And it's already starting to show, like, if we are measuring the tropics or if we are measuring in the mid-latitudes, we have always a high degree of complexity. So, okay, we can do it like from average of different flights, but we really wanted to do it by particle-by-particle basis, why we developed the PHIPS probe, that the idea was that we measure single ice crystals, we take images of single ice crystals and simultaneously measure the angular light scattering function of these ice crystals. So all the results that have been shown so far are from the PHIPS probe, but since there has been a lot of instrument development, we really couldn't have this feature working within the previous campaigns, but I really have to thank the Aristo campaigns, because only after those ones we really got it working, that we can really relate the single particle scattering phase functions for single ice crystals. So now I can also really prove my point, what I was trying to explain, that the shape doesn't matter. So now we can take individual ice crystals. These are from Aristo campaign. So here I chose only bullet rosettes, and here are the individual scattering phase functions of bullet rosettes. So we see still some features here, but if we average them, we get again a flat and featureless scattering phase function. The same story is if I look now different plates. So single plates might have some features, but on average in a cloud, we have again also a flat and a featureless scattering phase functions. And now if we compare the function from the bullets to the function of the plates, again, almost no difference. This is not now normalized, so just the shape is almost the same. So again, trying to prove the point, shape does not matter. But then the question is, what does it mean in global scale? These were some examples from campaigns, but we really have been trying to make now the first global picture of ice crystal complexity. Is it really important globally, and how do we see it? So just to now summarize, I add 2 more campaigns here. One is an Arctic campaign, and one is also a mid-latitude campaign. And now if we average over these campaigns, so we have tropical campaigns, we have 2 mid-latitude campaigns over Europe and over USA, and the Arctic campaign. And now I can look at the statistics of the complexity parameter average over all of the ice crystals we measured in this campaign. So again, here we have the threshold, here we have the tropical campaign, the 2 mid-latitude campaigns, and the Arctic campaign. And we see a pretty similar small-scale complexity all over the world. So it really doesn't make much difference if we're in the tropics or in the Arctic. We always have a significant degree of these surface roughness features. So now we have been able, for the first time, to prove with in-situ measurements that what satellites were already indicating that ice crystal complexity is important, it indeed is important globally seen. And again, we cannot represent the natural ice crystals with any simulations of pure pristine particles. And now again, if you look at the angular scattering properties globally seen, so to start, we have the laboratory results, the droplets and the smooth frozen droplets, and then our complex columns or spheres. And we add now the measurements from the Radiagon, so the tropical Cirrus. Again, we have the same angular light scattering function. Since we didn't have any angular light scattering measurements in the mid-latitude, I borrowed a data from our French colleagues from another mid-latitude Cirrus campaign. So it's a polar nephelometer with a slightly different wavelength, which might explain some of the deviations, but all in all, we have pretty similar, again, light scattering function. And if we now compare to the Arctic Cirrus, it really seems that all over the world we have only one cloud average angular scattering phase function, with an asymmetry parameter that is pretty low, 0.78. So then it was interesting to see what does it mean for now for climate modeling. What is really the asymmetry parameter that we assume in our climate models? So we did some collaboration with ETH Zurich that are operating the ECHAM-HAM model. And here I studied what is the parameters as asymmetry parameters in this model. These are these dashed lines. And then what I did is these are asymmetry parameter measured with one wavelength, but we were able to then extrapolate to get the asymmetry parameter. And we used the same microphysical model that we used here to get this parameter, and with different wavelengths, we created a parametrization for asymmetry parameters for the solar wavelengths. And now our results compared to those ones that are assumed in the models are, first of all, we assumed no size dependence, but we see also we have always a lower asymmetry parameter than in the model based on what we really measured in the field. So this was now the first guess. And it is pretty similar as seen in the satellite retrieval. So if we assume rough-net particles, we lose the size dependence on the asymmetry parameter. So we were really eager to see if we try to now parametrize our measurements, what it would mean globally seen. And if we know what we did is we did a run with this ECHA model using the parameterization it already had. The parameterization is not that bad because it already assumes some sort of ice crystal complexity. And then we did a run with our asymmetry parameter that we got from the field. And what we now get is a global difference in the short wave loud radiative effect of 0.5 watts per square meter. So this is the possible error that the current climate models, or at least this ECHA model, could be doing. And we see also locally it's almost -5 watts per square meter. And if you think that the aerosol radiative forcing is 0.9 watts per square meter, so you really have to ask, if you really want to get these forcings right, you really have to get these clouds first right. And yeah, we really need to know what is the cloud asymmetry parameter. Okay, so that was basically what I wanted to tell about the measurements, but I have still 5 minutes time. So I want to discuss then how to develop these measurements further. So I already talked about the polarized reflectivity measurements from the satellites and what the simulations are showing, because now the angular light scattering function, it was kind of saturated after we induce complexity within the ice particles, so it's a really bad measure if you want to study these features from the satellite or from in-situ measurements. But the polarization properties of ice crystals could still have some details of the ice crystal surface roughness. So what we have here is the backward scattering from 60 to 160 degree. This is the polarization component, and we have these different curves for different degrees of surface roughness. So if we have non-surface roughness, we have more features, but still inducing surface roughness does still somewhat change these polarization properties. So then the idea was, okay, why don't we measure now the polarized polarization properties by adding in the backward hemisphere, which is more sensitive for the surface features, also measurement, and that would be the next step, for example, for polar nephelometers. And that is something I'm, as a postdoc, right now working on, is including for in-situ measurements, these polarization measurements that we can now then compare directly with the satellites without using any assumptions in between. And that's not everything that we can do with angular scattering measurements. Satellite validation is one aspect, but I also really believe that measuring the particle light scattering not only with one channel, as normally cloud probes do, but with many channels could also give us new information on the particle microphysics. So for example, a difficult question is how do you discriminate ice particles in mixed phase clouds? So a lot of the times, or what we have until now done, is used these cloud particle images to say, okay, if we have large enough particles or they are asymmetrical enough, we can say, okay, these are ice particles. But if these ice particles are getting spherical, like in this case, it's really hard to tell if this particle is a droplet or if it's an ice particle. So basically, this method is limited depending on the instrument resolution to particles larger than 100 micrometers or maybe particles larger than 30 micrometers, as in the study of McFarquhar. But the question is how then we can identify the small ice crystals. And as I already shown, ice crystals, they have a scattering phase function that is in the sideward angles really differentiable from the liquid droplets. And it has so little variation due to this fact that atmospheric ice crystals are complex. So then I had the idea, why don't we use these features of the scattering phase function to do phase separation? And I found the best method to do this is just to look at the rainbow angle, because also if we would have an ice bow, it's slightly at a different angle as the rainbow. And yeah, to compare now the slopes of the scattering phase function between, let's say, 98 and 146 degrees. And I did some theoretical calculations where we have here these slopes for theoretical ice particles and slopes for theoretical droplets. And what I just wanted to show in this image, that theoretically we have a clear difference or clear separation of this rainbow slopes for ice crystals and for liquid particles. But that was just an idea that came last year. We haven't been able to prove it, but luckily we are currently measuring in the Arctic, in Arctic mixed phase clouds, and we are getting really promising results. And I wanted to shortly show you what we measured 2 weeks ago in an Arctic stratocumulus cloud at -3 degrees, where we measured now ice particles. Here are some images. So at these temperatures, we have a lot of columnar ice particles. We see here again hollowness and some nice features. But then what I did, because it's a single particle nephelometer here, I have for each single particle, the angular light scattering function is a really messy plot, but what I wanted to show you, so if we take a scattering function of each single particles, we can investigate the rainbow slope and then say automatically if this particle is an ice or if it's a liquid droplet without even looking at these images. So what we have here is the red ones are assigned to be ice particles. So we have these flat scattering phase functions, and these blue ones are assigned to be liquid droplets. And knowing the sampling volume, we can now, these individual counts, turn them into ice concentrations. So what we found out is that at really warm temperatures in these clouds, we had events where we have a really high ice crystal concentration. I'm not quite expert, but what I have been reading, this is pretty much the highest what I have found. Usually these ice particle concentration in Arctic mixed phase clouds are around 10 per liter. But now, because we are not just measuring the biggest particles, but we are also measuring these really small ice particles down to 10 micrometer, we get really now higher ice particle concentrations. And we indeed, for example, at the top levels of the clouds, the scattering phase functions, they have a lower intensity. So we really do have a lot of small ice particles in these clouds that we have maybe previously missed because we couldn't detect them. And yeah, so this is something to develop in the future, and I'm really happy that I can also use this method in the upcoming Socrates campaign to now also derive hopefully reliable ice particle concentrations for clouds in the Southern Ocean. But this is not the only thing that the PHIPS can do. It's a feature of the instrument is also that a trigger detector is sitting at 90-degree angles, which means if we have a droplet, we have a minimum here, and not the smallest droplets are not triggering the instrument, whereas we can trigger small ice particles that have flat scattering phase functions. So really we start to image droplets, like here, only up to 60 micrometers. So we can also now use this instrumentation to study secondary ice processes. Here are examples of the images of cloud particles in cloud top. So what we have here is these rimed particles and coexciting with large droplets. And we have also these, I'd say, pristine, non-rimed vapor-grown ice crystals that have to be produced from some sort of secondary ice processes. And now we can take this ice sample concentration that we measure and try to relate them, for example, for cloud top layer, to these concentrations of these larger droplets. And we see a clear correlation that was also discussed already in the 90s by Director Hobbs et al. So really, this is also a new way to really start to investigate also secondary ice processes. Okay, there's not a lot of data here because we have only so many flights, but I really hope we can get some few more data points here. Yeah. So then to go to the summary. So we investigated the ice crystal complexity in the laboratory, where we showed that the ice particle angular scattering function is independent of the ice crystal shape. We also did field studies where we found that all over the globe we have a significant degree of ice crystal complexity that led what I call a global angular scattering function, which included into the global models showed that we still have a huge uncertainty in determining the short-wave cloud radiative effect, that indeed ice clouds could have more negative short-wave effect than previously thought. And then I also discussed how we can advance our measurements by including, for example, polarization measurements. But one of the biggest problems what I see in these results is that we are only measuring with one wavelength, and we have to do some hocus pocus to get parametrization for the global climate models. So what we really need is spectral resolved measurements of cloud radiative properties to give right answers for the modeling community. And here I want to thank you for your attention and here's some questions.
We do have time for some questions. We'll use the microphone for people down at RAF who are listening.
So that's a very interesting outcome to say that it's in some ways it seems very nice that we can reduce to just a complexity parameter. But one thing I was wondering about is particularly when you integrate this asymmetry parameter into the models, aren't you assuming that the particles are randomly oriented? And don't we know that there definitely are particles that orient in the case of cirrus clouds and especially plates and columns? And how would that impact the asymmetry parameter?
Well, basically the asymmetry parameter what we gave is based on the atmospheric measurements. So of course we have, no, we don't have because we are measuring it an in-situ probe. But what we showed is that then if we have oriented crystals, then it's more habit dependent of how they are scattering. But if we now induce these complexities, for example, surface roughness on top of them, then we get also rid of these effects, or not completely, but majorly these effects of orientation. So then it might not be such a problem afterwards to not assume oriented crystals. And yeah, oriented crystals, it's also a question like in which type of clouds they are appearing. So of course you need plates, plate-like crystals, and yeah, I'm not maybe the expert of how frequently you have it in the atmosphere, but I wouldn't see it maybe such as a critical feature. More critical, I would see the other assumptions that we are doing by extrapolating over the sizes and over the wavelengths. They are more critical issues to solve.
Can you describe your last clouds a little bit more with the large droplets in it? What air were they formed in? Was it stable or a moist adiabatic, well-mixed cloud? Or?
Yeah, these are basically all of the measurements from the campaigns. So we had situations where we had well-mixed clouds. Yeah, usually they were well mixed. There were also some situations where the mixing was not so good, and it's too early to say any conclusions, but the more well mixed clouds, they had these higher ice crystal concentrations. But then on the other hand, I was also trying to study like how inversion profiles over the cloud would affect it, but we also got, the cases were really, we have different cases, but we couldn't find any clear correlation between the mixing or with the inversion or with the temperature of the ice crystal concentrations. The only correlation what I right now found is for these droplet concentrations. But as I said, this data was gathered 2 weeks ago, so there hasn't been that much time to analyze it.
And was it done over the ice or over open water?
These were, most of them were over the ice. There were a few cases over the open water.
I was just curious, this may be a bit naive, but on some of your plots, you had a couple on the scattering angle, you had lines that came from some, earlier model. What is is there a theoretical basis that would allow you to sort of calculate or predict that relationship of scattering angle for, particles of different size but rough surfaces?
The scattering angle of...
So, could you predict the scattering angle for these particles from theory and calculations, or is that completely an empirical result?
You mean if you could reproduce the measurements using theoretical calculations, or which
maybe
slide?
If you go back a couple of slides to where you had the scattering, like right there. So the blue and the red lines that go on there, are those from theory?
Yeah, they are from theory, so they're just from Bing Yang's database. For different ice crystal shapes. So could be... Okay,
I see. So that was what I was curious about. But and for different shapes, they similarly predict that the shape doesn't matter that much?
Well, you still have some differences. In the functions for different shapes. Okay, this is maybe not the best one because we have here columns and plates that are just with different aspect ratios, like hexagonal columns. But we still see like at different points these halo features, or we have here in the backward hemisphere much more differences. And we really see it now in the asymmetry parameter that it's different for different shapes, and it's also quite hugely different. That's why the modelers thought previously that it's really important to get the shape of the particles right, because we get a totally different asymmetry parameter. So that's I'm trying to prove that we don't have to care about the shape, because then if we go to the rough particles, maybe not in these models, but in the measurements we get really rid of the variations in the asymmetry parameter. But that's only if we average over the whole cloud. If we're talking about single ice crystals, we still see a lot of differences, but in average we still only see the same scattering behavior.
Thank you, that helps a lot.
So kind of a follow-up question. So you're saying that for radiation, the shape doesn't matter too much, right?
In the case there's surface roughness. But if there's no surface roughness, then it really does matter. And this is also the question. I'm trying to be a bit of provocative in this talk, but of course you have different situations. You might have these outflows that are really sublimating at tops, and then you might have really these spherical ice particles that would have then a totally different scattering properties. So of course we should also find situations where we can prove ourselves wrong, where we say, okay, it's not only the same asymmetry parameter all over the world, but that's also what I'm trying to say here is in-situ measurements, they are always snapshots. We get into one situation and get some sort of measurements, but really to globally say what is the truth, you need then again the satellite measurements, but then you need the in-situ measurements to validate the satellite measurements. So it's kind of a loop, the mouse chasing the cat and other ways. To get the global picture.
And so far you haven't found any in-situ cases where you see mostly smooth particles?
We had one case in the MacBex campaign where, because I showed you the laboratory results of these spherical ice crystals that are also optically spherical, and really to show this sort of scattering phase function. And in MacBex we had one convective outflow where we really did measure from the scattering patterns. We had these ice particles with concentric ring patterns, and a colleague here in MCube published a paper where he tried to then from these scattering patterns, analyzed the partial scattering phase function, and he only saw a difference in this partial scattering phase function in this case where we had these spherical particles. But since we didn't have a polar nephelometer, we don't know what it really was the whole scattering behavior, but there was a strong indication that there are special cases where we have totally different angular scattering properties.
Thanks.
Okay, if there are no more questions, I think we should thank our speaker again. Thanks everyone for coming.